Okay, this third lesson we're looking at a few other properties of waves. So first of all, reflection. Alright, so there's a few videos here. These things show the reflection and the waves and the interference and all that I'm going to discuss in this lesson. So there's a few things, videos there that help you with that stuff. Alright, and they're on the website, of course. Alright, so reflection is the first thing that we're going to look at, and first of all, waves in one dimension. Alright, so that's like waves on a slinky or something like that. Now, the behaviour of that wave, what happens with it depends on what the end of it's like. So here's a diagram that shows that. Alright, so in this diagram it depends on whether, as to what happens on the reflection, as to whether the end of the spring or string is fixed or whether it's not. So if in the case on the left here that it is fixed, you can see when it comes in and comes out, you can see that the wave flips over. Alright, so that flipping over, so fixed end, the wave flips. Now, what that's actually called in physics is called a change of phase. Alright, so change of phase if it flips over, and to be even more technical, it's by half a wavelength. Alright, so as you can see, that peak turns into a trough, and remember from the previous lesson, peaks and troughs, one peak and one trough is a whole wavelength, so peak to a trough is half a wavelength, so it's change of phase. Now, if that end, like this one here on the right here, if that end is free to move up and down, then it's different. As you can see, that end, because it's free to move up and down, as that peak comes in here, you can see that it's moved up there. And so it's able to move up and down. And so we would say that there's, no phase change in that. All right. So a little bit more, words on that in your notes, of course. All right. The next thing, of course, is that you could have a number of waves that come together and interact with each other, and so that's what we call interference, and superposition is another word that's used here with this. So the waves will interfere with each other if you've got two or more waves coming to the same place at the same time. So then superposition is what happens. So here's a diagram here. All right. So here we can see a couple of wave pulses, one coming in from the left and the other one coming in from the right. And then when they meet, you've got the one in from the left that's like that, and then the one in from the right that's like that. It's supposed to have changed some colour there. Here we go. And then the one from the right that's like that. And essentially what we have is we have these bits that add up. So you've got that blue bit and you've got that green bit, and you add them together and then you get the sum of those, which looks like that. So superposition. Alright, and so when they're right bang one over the top of the other, and that's what this diagram here is showing, each of them's got an amplitude of A, and so the interference, or the result of those, we now have an amplitude of twice that, 2A. And then of course they then keep moving, and they actually do not reflect off each other. Sometimes people think they reflect off each other, and you can show that they don't actually reflect off each other pretty simply with a slinky, sending a couple of waves of different sizes towards each other. Alright, so they pass through. So at the time when they're at the same place, they interact or superimpose. So they add up, if you like, and then you get a bigger wave. Now, that leads us then to the two different types of interference or superposition. Alright, and this bit is in your notes. So it's constructive interference. So as it says there, it occurs when the crest of one meets the crest of another. Alright, and so here's our two waves, wave 1 and wave 2. So wave 1 has an amplitude of A, wave 2 is twice that of 2A, and so when each of these crests corresponds with each other, and here's a nice dotted line there that you can look along, so you've got A and 2A, and so what you end up with is constructive interference, constructing a bigger wave, and so the wave now has a height of 3A. Alright, so that's the first type of interference. Now if you can construct or create a bigger wave, you could perhaps destruct or create a smaller wave. Right, and here's a diagram that shows destructive interference. Alright, I left the text off the top of this one, I think. Oh, no, I didn't. No, I didn't. It's just hidden under my menu that I've got when I record this. So again, we've got two waves. We've got one coming in from the left, one coming in from the right, and you'll see the one on the left we've got a peak, the one on the right we've got a trough, and so they are out of phase, if you like, by different phases, a trough and a crest. Alright, so when they come to here in the middle, as it shows, if they're exactly the same wave, you've got one up there and you've got the other one down there, and they interact with each other, interfere with each other, and because one's positive and the one's negative, you get zero. So in that case, they've kind of destructed, and you've got destructive interference, and so it's just a flat there. And then, of course, they will then move on through each other and pass out, and there they'll be. Now, in real life, it's going to be a lot more complicated than that diagram. Here's this diagram underneath here. Shows one that's a little bit more complicated, but it can get far more complicated than that. Alright, so you've got wave 1 and wave 2. And again, there's different bits that interact with each other, and so you end up, as you can see, with that more complex wiggly wave. Alright, so that's reflections in one direction, a dimension I should say, so that's like on a slinky spring or something like that. Alright, we can also have reflection in two dimensions, and reflection in two dimensions, that would be things like, you know, water waves, things like that. And we've got some videos there too, record tank videos that show you these. Alright, so essentially what happens is very similar to what happens in one dimension. So if we've got a barrier here, like a brick wall or something like that, and we've got some waves heading in. So on this diagram, we're kind of looking down from the top, and the waves are heading in this way. So these lines here, what they represent is the crests. All right, so when we draw a diagram like this, we show the wave crests. So they're going in, they're hitting the barrier, and then they're coming back out. And so you can see those wave crests coming straight out. So the thickness of the lines there is just so that you know which ones are going in and which ones are going out. All right, they don't actually change their size or anything when they reflect off the barrier, theoretically, unless of course they lose some energy. All right, so there's lots of things that will reflect in this particular way, you know, microwaves, radio waves, etc., etc. All right, so straight in, straight out. But if we were to then get this barrier and twist it so it's now on an angle, and they're not going straight in and straight out, then what you get is this. All right, so here's diagrams that showing you what happens there, and of course in those videos show you this as well. All right, so over here on the left hand, so we've got the incident waves. So there's our wave crests. So our incident waves are heading in this direction, and then they reflect out, and they reflect out in that direction. All right, so there's this line that we put down the middle, imaginary line that goes down the middle here, and it's called the normal, and that is at 90 degrees. So normal to the surface, 90 degrees to the surface. All right, it's just like, you know, tangents and normals in methods when you get to it. So it's called a normal because it's at 90 degrees to that surface. So if we simplify that diagram and take the wave crests out and just put the directions, and that shows this one here over here on the right shows that. So you've got your incident ray coming in. Now, if we measure the angle from the normal to the incident ray, we call that the angle of incidence. And if we measure the angle from the normal to the reflected ray, we'll call that the angle of reflection. Then what we know and what we find out when we do that is we find out that the angle of incidence and the angle of reflection are the same. All right, so important to remember, when we measure that angle of incidence, it's the direction of travel, so the direction of propagation, and the normal there, so it's this angle in here is the one that we are interested in for the incidence, and this one here that we're interested for reflection, and the key thing is that they are the same. All right, so that then leads us to what happens if we've got a rough surface. So here's our rough surface. Lots up and downs because lots of things are rough surfaces. So what happens? So here's our light source, if you like, up here, shooting down light rays in all sorts of directions. Now, when we talked about the normal, right, being at 90 degrees to the surface, so in this reflection here, which we're calling diffuse reflection, all right, so because it's diffusing, if you like, the angle of incidence and the angle of reflection are still equal, but because of the surface it changing, the normals to that surface at the different places are different because of the wiggly shape of the surface. All right, so angles of incidence and angles of reflection, if I drew these properly, would be, I haven't drawn that normal very well, have I? Should go more there. All right, so the angles of incidences and the angles of reflection are still the same. So that doesn't change, but because the surface itself is changing, then you get, instead of, like on a mirror, going in one direction and out in that one direction, comes in one direction, but then it goes all over the place in terms of after it's reflected off the surface, depending on where that surface is. All right. So the next and the last bit is what we call resonance. All right, resonance. We don't need to know a huge amount about resonance, other than everything has a natural frequency. All right, so, you know, a guitar string or whatever, even a glass, will have a natural frequency that it's happy to vibrate at. Now, the thing is, when you get that natural frequency, if it's vibrating caused by something else, and you get that natural frequency, you get what's called resonance. And so what happens with resonance is it increases, if you like, the volume. All right, so acoustic guitar, for example, we've got our acoustic guitar, looks like that. There's our neck with our strings, and our acoustic guitar, of course, has a hole in it in there, and so that sound goes in that hole, and resonance occurs inside the body of the guitar, and it sounds a lot louder than it is. All right, so it's used, as it says in your notes there, a lot in musical instruments. All right. Okay, so it's not necessarily the body, well, it isn't the body of the guitar that's making the vibration, it's the string that's making the vibration, and the body of the guitar resonates and makes it louder. All right, there's a couple of cool videos there on resonance. So there's a cool one where the wine glass gets broken, and there's also another one which is very famous about a bridge in the wind. So you should have a look at those. All right, so that's it. That's another couple of few definitions of things. All right, again, a couple of those things that, you know, it's just reviewing from last year. Again, if you're not sure about anything, make sure you ask, and then there's some text questions for you to do.